Students, I hope you had a lovely half-term break. Today's topic is distance time graphs. Now, our learning objective from that is going to be able to interpret a distance time graph and calculate speed. Here are the starter problems. Spend no more than 10 minutes doing them. Pause the video to get them done. Resume the video to check your answers. Okay, so for our first question, it asks you to find the mode, which is to find the number that is repeated the most, and that number is 13. It's been repeated 3 times. The next question says we need to expand 2 times 5 minus x, so we can set up our grid. 5 on top minus x on top, and then 2 to the left. Then we can multiply. 2 times 5 is 10, 2 times minus x is minus 2x. The two terms that have come into our boxes, that's what will give us our answer. So it's 10 minus 2x for our final answer. Then for number 3, y is equal to 3x squared, and we need to work out the value of y when x is equal to 2. So y is equal to 3x squared is equal to 3 times x, because x times x is x squared. So we'll substitute 2 for x, so we'll end up with 3 times 2 times 2, and when we work that out, 3 2 is 6, and 6 times 2 gives us 12. Our next question says work out 10 times 5 minus 3, so we'll have to work out our brackets first. 5 minus 3 will give us 2, and then we can do 10 times 2, which is equal to 20. Then our final question says we need to simplify this expression, so we look for like terms. We have 1x here plus 4x, and that will give us 5x, and then we have a minus 3y here and minus 4y, so minus 3y minus 4y, which gives us minus 7y. All right, let us move on to the lesson. Distance time graphs. So what is a distance time graph? Distance time graph represents a journey. Okay, the vertical axis, that's our y-axis, will represent the distance from a starting point, and the horizontal axis represents the time taken for the journey. So if I just make a little sketch, this is my x-axis or my horizontal axis, and it will always represent time when we're looking at a distance time graph. And the vertical axis, which is my y-axis, will always represent distance. Okay, so whenever we have a distance time graph, distance is on the vertical axis and time is on the horizontal axis. The distance time graph shows a journey, as I said earlier, and here's an example of a distance time graph. Now, what does the slope of the line tell us? The slope of the line, or the gradient of the line, or the steepness of the line, gives us the average speed of an object on a distance time graph. So the distance time graph, when we look at our slope or the gradient of the line, it will tell you how fast the object is moving. Now, the steeper the line is, the faster the object is moving, the faster the speed. Okay, so I'd like you to pause the video and make a note of this, then resume the video when you are ready to move on. Let's look at these examples of distance time graphs. Each of the graphs is showing a journey for an object, okay? And in the previous slide, or on the previous slide, it said that the steeper the line, or the steeper the slope, then the faster the object is moving. So if we label these graphs 1, 2, and 3, the steepest line is on graph 3, so it means that the object is moving fastest based on the graph, right? And then number 1, this graph is showing that the object is moving the slowest based on the graph when we compare the 3. Now, when we have a straight line on a distance time graph at a slope, it is telling us that the object is moving at a constant speed, or some say steady speed, which means that if the object is moving at 20 miles per hour for the whole journey that we're seeing from start to end, the object is moving at 20 miles per hour. And so for each of these graphs, we have a straight line at a slope, right? So then all three graphs are showing constant speed. Please pause the video and copy this information. Resume when you're ready to move on. Some other examples of distance time graphs. With this graph, did I say close? Here we have a distance time graph where each part on the distance time graph has a different color. Now, this distance time graph is representing an object's journey. Now, can you tell what is happening at each part on the graph? So is it constant speed? Has the object stopped? Has the object moved faster or slower? Has the object returned to its original position or starting point? Can you tell for each color what is happening? Each color on the graph, what is happening? Pause the video, make a sketch of this graph, spend no more than 10 minutes to sketch the graph and label the different sections and say what is happening. Once you finish, resume the video, then you will get the answers for the question. For the first part, the object is moving at constant speed from its starting point. Okay, so it started here and moved, we have a straight line up to here, so it means constant speed. Then we have the green section where it stopped. All right, if you have briefly or not doesn't matter, but that green section shows that the object stopped moving. Then the object moves further away from its starting point, so we can see where it's gone at a bigger distance than the first movement, and so we say it's moved further away from its starting point. However, the purple section would be at a lower speed than the yellow section, because the yellow section is steeper, which means you will have been moving faster in that section. Then for the red section, it's showing that the object returns to its starting point at a constant speed. For here as well, we could say that although it's a lower speed, it is still constant, right? So we could say it moved further away from its starting point at a lower constant speed. Any changes that you need to make, please pause the video, make your corrections, and then resume when you're ready to move on. Now I'd like for you to pause the video again, and I'd like you to match the graphs with the statements in the orange boxes below the graphs. So pause the video, spend no more than 5 minutes doing this, then resume the video to check your answers. Okay, so for our first graph, it would match with a car remains parked in a car park. Notice the graph shows a horizontal line which tells that the object is not moving, so the best description would be a car that is in a car park. It's not moving, it remains parked, so it's not moving, right? For graph 2, it would match with a runner runs at a steady pace, so we're seeing where it's going at a steady pace from a starting point, going up to a distance, and then it turns around and runs with the same speed back to where it started. Okay, so remember I told you if the line is going downwards from left to right, this section here means that you would have changed direction on the distance time graph. You're going back to your starting point. All right, then our final, of course, will be a motorbike travels away from home at a steady speed. So we're seeing it's moving from the starting point, straight line showing constant speed, so it moves away at a steady speed. Here's a distance time graph of John's journey by car. So we are going to write a story to describe his journey. Now there are 3 parts on our distance time graph for John's journey, so we need to describe these 3 parts in as much detail as possible to see how fast he's moving, if in terms of is it constant speed, or is he accelerating, or has he stopped, or has he returned to his starting point. We need to put as much detail as possible. How long did he stop for, etc. So let's look at our first part of the journey. The first slope that we have, the distance is 0, so he's at a starting point, not moving is there. Then we have our slope going up to 20 miles, and that slope is a straight line, which tells us it's a constant speed. And in order to get to 20 miles, he would have done that over 30 minutes. So it took him 30 minutes to drive 20 miles. And so for the first section of our distance time graph, we could say that John leaves home, he drives at a constant speed for 30 minutes, right? And that would have gotten him to 20 miles, but I'm going to put that in the second part of the description. Now for the second part of the journey, we can see that he has stopped. We have a horizontal line on the distance time graph, so that tells us that that John has stopped. Now he has stopped 20 miles away from home, right? Because he got up to 20 miles and then he stopped. And we could say that he stops at a friend's house, or he stops at a park, which is 20 miles away. Okay, we can be as creative as we want in terms of where he stopped, but wherever he stopped, it's 20 miles away. Okay, and we also need to say how long he stopped. So if we check for the section where he stopped, it's from 30 minutes to 75 minutes, so he would have stopped for 45 minutes. For the third part of the journey, we can see we still have a constant speed because it's a straight line for the slope. Alright, and it's telling us that he's going back to 0, which is his starting point. So we could say he then drives home at a constant speed and arrives 45 minutes later. Now let's see why it's 45 minutes later. From 75 minutes, that's the amount of time that has passed since he left home, and then he got home 120 minutes later from the time he left home. So 75 minutes to 120 minutes, the difference is 45 minutes. So it took him 45 minutes to drive home, but he did that at a constant speed. Now let's look at reading our distance time graph. So again, your distance time graph, distance is on the vertical axis, time is on the horizontal axis. We also need to make note of what the units are. So the distance was in meters and the time is in seconds. So our first question is, how many seconds does it take to travel 60 meters? So we'll have to find 60 meters on our graph, which is here, and then come across to the graph, then come down to find out number of seconds, and that looks like about 75. So we say 75 seconds to travel 60 meters. Right. Next question says, how many meters was traveled in 50 seconds? So we need to find 50 seconds, then go up to the graph and then go across to find out how many meters would have been traveled in 50 seconds, and that's 40 meters. So be careful with reading your distance time graph. Here's another distance time graph example. We need to use the distance time graph to answer the following questions. Now, it says how long was the journey, so we need to see how much time it took for the journey. Now, we would have started here, or starting point, and we'd have traveled to this distance. How much time did it take to do that? It took us 60 seconds. But then on the second part of the journey, we returned back to our starting point, which took another 60 seconds. So it gives us a total of 120 seconds for how long the journey was. The second question says, what's the total distance traveled? So from the starting point to the top, we would have traveled 30 meters, and then to return back to our starting point, that's another 30 meters. So together that gives us 60 meters. Here's a distance time graph question. It says the graph shows the journey of a cyclist, and I need you to pause the video for no more than 6 minutes. Answer the question based on the distance time graph to the left. Once you're through, resume the video to check your answers. Okay, so for the first question, I said, when did the cyclist leave home? So we can see this is where the cyclist started. Notice the time of day, they've given the time on a clock. So the cyclist left home at 8 a.m. It says, for the next question, when did the cyclist return home? We can see this line shows that he is returning home, returning back to his starting point. He arrived home at 5 p.m. It says, how far away from the home was he at 10 a.m.? So we'll find 10 a.m. and go across the distance. He would have been 20 kilometers away from home. Then it says, how far away from home was he at 11 a.m.? He was still 20 kilometers away from home at 11 a.m. It says, how far away from home was he at 2 p.m.? He was 60 km away at 2 p.m. And how far from home was he at 3 p.m.? So we go up again and we see that he is still 60 km away from home at 6 p.m. at 3 p.m. sorry. Then they say, at what times did he take a rest? Now here is where we see that he has stopped, so that would suggest that he is resting. And so the times that he took a rest would have been between 10 and 11 a.m. and also between 2 and 3 p.m., which would have been suggested from C and D, where he was 20 kilometers away from home between that hour of 10 a.m. and 11 a.m. and then he was also 60 kilometers away from home between the hours of 2 p.m. and 3 p.m. So that would suggest where he was resting. Now it says, how far away from home was he at noon? So if we come to noon to see how far he was away from home, right, we could say 33 kilometers away from home at 12 noon based on this diagram, right? Then it says, how far away from home was he at 5 p.m.? He was 0 kilometers away from home. Why? He was at home. Okay, he was not away from there. So let's move on to the next slide. Look at drawing a distance time graph based on a scenario that is given. So here's our scenario on the right. It says Jim walks at a constant speed for 10 minutes to his friend's house, which is half a mile from his house. He stayed there for 20 minutes, then returned home walking at a constant speed. He got home after 15 minutes. So we need to see how long the journey took him. 10 minutes to walk to his friend's house. He spent 20 minutes there, and then he walked home for 15 minutes. So that's a total of 45 minutes. So on our time, the time is given in minutes, so we'll put that in. The total journey took 45 minutes, so we need a scale that will take us to 45 minutes. So here's a scale that will work. And of course, you can choose your scale depending on the axis that you have to work with. So I'm putting those in. Right, and then it says that he walked to the house, to his friend's house for half a mile. Didn't go any further than that from his house. So this should be okay if we do the distance in miles, and then that would be 0.5 of a mile, and so that would be 1 mile. All right. So it says that from his house he would have traveled at a constant speed for 10 minutes, and that would take him to his friend's house, which is half a mile away from his house. Constant speed, so we need a straight line from the starting point to his friend's house, which is half a mile away. He spends 20 minutes at his friend's house, so from 10 minutes add another 20 minutes, so that will take us 30 minutes, straight line going across, right? So from the start of his journey, we'll end up to 30 minutes for the time that he spent at his friend's house and walking to his friend's house. So the next bit is that he will walk home at a constant speed, and this takes him 15 minutes to do so. So from 30 we need to put 15 minutes on to that, which would make 45 minutes, and it's walking at a constant speed, so a straight line to 45, and that would be your distance time graph for Jim's journey. Now we're going to look at finding speed from a distance time graph. Now the first thing you need to know is that speed is equal to distance divided by time, and we can achieve that from our magic triangle, where we have speed would be equal to distance over time, which is distance divided by time. So that is our formula. Now on the earlier slide, we spoke about what the slope of a distance time graph represents, and I asked you to make a note of it in your books, and I'm doing it here again, where the slope represents how fast the object is moving. And so if we're going to find the gradient, which is the slope of the line, then that is going to give us how fast the object is moving, which in other words means the speed of the object. Now when we found the gradient of a straight line, we would normally take a right angled triangle, which we did in previous lessons, and we would take the height of that right angled triangle and the base of the right angled triangle and divide them. So it would have been the change in the height, and we divide that by the change in the base, and that would give us our gradient or slope, and we know that that will tell us how fast our object is moving. So let's put that into practice. But before you do so, can you pause the video and make a note of the information here? Resume the video when you're ready to move on. Let us explore finding the speed of the distance time graph here. So we're going to do it two ways, the same thing but just using different values. So it's a straight line, so we can find the gradient because the slope of the line, or the gradient of the line, is going to give us the speed of the object. And so I could take this right angled triangle from here to here, straight line, that's my right angled triangle there, and the change in height is 80 because we're going from 0 up to 80, and that is miles. And then for the base of the triangle, our change in time is from 0 to 1, which is 1 hour. So if we're going to work out our speed, it's going to be the distance, that's the height of the right angle triangle, and then divided by the time from the right angle triangle. The change in time is 1 hour for the right angle we selected. And so we just divide them and we get 80 miles per hour. Now we didn't have to select that particular triangle. We could have done a different triangle, and so we're going to look at doing that and see if we get the same answer. So then, what if I decided to create my right angle triangle from this point and this point? So there we go. So we have a smaller right angle triangle. This time the change in the height of the triangle, or the height of the triangle, is now 40 miles. And then from here to here is halfway of the 1 hour, so it's half an hour, right? So if we're going to work out the speed, it's gonna be the change in the distance, or the height of the triangle, which is 40 miles, and then the time for that right angle triangle, for the base of the triangle, is half an hour, which is 0.5 hours. And so 40 divided by 0.5 will give us 80 miles per hour. It doesn't matter the right angle triangle that we use, as long as we have the correct height of the right angle triangle and divided by the correct time for the right angle triangle, then we can divide them and get the speed. Now our speed is gonna either be in miles per hour or kilometers per hour. So whenever you're writing your time, make sure it is in terms of hours. So it's either half an hour. There's another example. 1 hour, 2 hours. Just make sure it's in terms of hours in the following distance time graph. So I can choose to select this point and this point to create my right angled triangle. And so I need the height of my triangle coming from 0 to 80, so it's 80 miles. And then for the base of the right angle triangle, it is 2 hours. So for the speed, we do the distance, which is the height of our right angled triangle that we have, and the time was 2 hours. So when we divide them, we get 40 miles per hour for the speed. And that's how fast the object is moving. Now for a final example, I'd like to pay close attention. We have a few questions to have a look at. So we have a distance time graph for train service between Farnham and Petersfield. Okay, now A says how long did the train stop in Alton? Now if we look here is where Alton is, so we need to find out how long the train stopped. Now from this point to this point it's 1 hour, and that's split into 4, so 60 minutes split into 4 would be 15 minutes. So therefore means that the train would have stopped 15 minutes at Alton. It says, how far is it from Alton to Petersfield? So the train would have started at Farnham 0, okay, up to Petersfield, which is 20 miles away from Farnham. However, so how far is it? That is Alton from Petersfield. So Alton is at 4 miles from Farnham, and then going up to Petersfield, that's takes us to 20 miles. So we'll subtract 4 from 20, and that would give us 16 miles. The next question says we need to work out the average speed from Alton to Petersfield. So Alton to Petersfield, we need the average speed. So we're at Alton, going to Petersfield, we need that right angled triangle, and we're going to work out the speed. So we need the height, okay, and that was 16 miles from Alton to Petersfield. And we also need to work out the time. Now it's half an hour, that is from 9 a.m. to 10 a.m. here, and then it's halfway. So it's half an hour to travel from Alton to Petersfield. So to find the speed then is going to be speed equal distance over time, and that's going to give me 16 for the height of the triangle from Alton to Petersfield, and the time is 0.5 hours. And so when we divide that, we get 32 miles per hour. For D, it says the average speed on the return journey. So here's the return journey. That's Petersfield back to Farnham. So we need this right angled triangle between Petersfield and Farnham. We need the height of that triangle, and that's 20 miles. And then the time it takes to do that return journey is 1 hour. So our speed, which is distance over time, would be 20 miles over 1 hour. 20 divided by 1 is 20, so we get 20 miles per hour. Okay, the final one says the average speed for the whole journey. Now when you're asked for the average speed for the whole journey, we need the total distance traveled divided by the total time. Okay, so the speed is equal to distance over time. What's the total distance traveled? The total distance traveled would have been 20 miles from Farnham to Petersfield, and then 20 miles back from Petersfield to Farnham. So that will be 40 miles, and the time to do that was 3 hours from 8 a.m. to 11 a.m. So we'll divide 40 by 30, and we'll get a total, we're gonna get 40 divided by 3, we're gonna get 13.3 miles per hour when I round it to 1 decimal place. Turn to try some questions. I'd like you to go to show my homework. Follow the instructions for what you need to do for this task. Spend no more than 20 minutes doing the questions, then mark your work. Once you're through, please send me photos of the marked copy and I will give you feedback. For your graphs that you are going to draw, please ensure that you are using ruler and pencil to draw your best graphs, okay? Now, I look forward to seeing your work. Thank you so much and enjoy the rest of your day.